So welcome in 1 minute we'll start. So welcome to the session. So in this session, what we do is we'll go through the topic, that is linear equations. That is what we call as system of equations which are linear, and the linear equations are of two types. One is non-homogeneous, other one is homogeneous. Here we'll discuss or we'll see how to solve linear equations, whether it is a homogeneous or non-homogeneous, with the help of matrices. Okay, so here so now to begin with, now consider the linear equations a11x1 plus a12x2 plus a1nxn equal to b1, a21x1 a22x2 plus a2nxn equal to b2, and so on. Now it is a generalized form, otherwise it is as if we write x plus y plus z equal to 5. Right. This is one equation, and other one is 2x plus 3y plus 4z equal to 8. Right. Okay. So these are the equations. Right. So here why they are called as linear equations, that is the first one. Actually this is very essential to understand the term linear equations. So linear, why they are called as linear equations is, so if you see here the term, this term if you take, it is having x whose power is 1. Here we had a term y, that is variable here, variable y whose power is 1, z whose power is 1. Right. So then this is called as a linear equation. Suppose if it is something like xy plus z equal to 4. So then we cannot call this as a linear equation. If you see this term, so here the power of this term, here x power 1, y power n, on the whole it is power, the power of the term or degree of the term is 2, right? So then it becomes a non-linear equation. Right? So that is the difference between linear and non-linear. So now this is the generalized system of equations. Right? So how to solve the system of equations? Right? So here solving the system of equations with the help of matrices. Otherwise, in high school mathematics, we have seen how to solve these kinds of equations. Just eliminating x, then eliminating y, finally z value. Right? So here, how to solve these system of equations with the help of matrices. So first what we do is we write the system of equations in a matrix form as Ax equal to B. So very simple. So A is nothing but, so whatever the coefficients are there right here, A11, A12, like 2x plus 3y plus 4z, like. So all the coefficients, so we had in this matrix, that is called as a coefficient matrix. So this is a column matrix X, where what are the entries here? All the variables here, x1, x2, so on, xn, right? All are the entries in the column matrix. Equal to, so this is another column matrix, b1, b2, so on, bn. So this column matrix contains all the constants here, b1, b2, so on, bn, right? So first thing what we have to do is we have to write the system of equation in matrix form as Ax equal to B. So here that is I think repeated, Ax equal to B, where B is column vector consisting of b1, b2, so on, bn, and x is another column vector consisting of all these variables x1, x2, x3, so on, xn, right? Right? So A is a coefficient matrix. So one more matrix, one more term we use, that is augmented matrix, right? One more term we use, that is augmented matrix. So he has shown here augmented matrix is nothing but the matrix A, that is coefficient matrix, and accompanied by the column matrix consisting of b1, b2, and so on, bn. Right? So now before trying to solve, before discussing how to solve this system of equations, so let us see difference between homogeneous and non-homogeneous. Then we'll see what kinds of solutions, what types of solutions we can expect for a linear system of equations. Then we'll get into how to solve the given system of equations. Now here if you see, here Ax equal to B is what we have seen, right, when we take the system of equations, right? So Ax equal to B is called as linear and non-homogeneous. So if you see here x1 plus x2 equal to 2, 2x1 plus 3x2 equal to 5. So actually here this 2 and this 5 are making this system of equations as non-homogeneous. Right? So that means actually to understand this in a geometrical way, what it says is they are not passing through the origin. If you take this is a straight line, right? This is a straight line, right? And it is not passing through origin. This is another straight line. It is also not passing through origin. Suppose this Ax equal to 0. That means this B is there, no? B becomes 0. Then they becomes linear and homogeneous system of equations. So like my x1 minus x2 equal to 0, minus x1 plus 2x2 equal to 0. That means you won't have these constants, right? So they are zeros. Right? That means Ax equal to 0 is homogeneous, Ax equal to B is non-homogeneous. If you see here, this system of equations, if you think in terms of geometrical representation, this is a straight line, this is a straight line, and both passes through the origin. So this is another understanding we need to have, that is linear equation categorized into homogeneous as well as non-homogeneous. Then, so what kinds of solution or what types of solutions we can expect when we try to solve this, right? That is one. Suppose first we'll take non-homogeneous, right? So first example we'll take this x1 plus 2x2 equal to 3, 2x1 plus x2 equal to 3, right? So what is meant by a solution? We know how to solve this in our school math we learned. So multiplying this by 2, then subtracting x1 goes, then we'll get x2 value. Or otherwise, if you see here, if I put x1 equal to 1, x2 equal to 1, right? So x1 is 1, that is 1 plus 2 into 1, that is 3. 2 into 1 plus 1, that is 3. That means these values x1 equal to 1, x2 equal to 1 satisfies both the equations. That's why this is called a solution. And if you try, you won't find any other combination of x1, x2 which never satisfies this. Right? So that means if we try to understand this geometrically, right, like this. So this is a straight line, this is a straight line. Suppose if we plot like this, these two straight lines intersect at a point 1, 1, which is the solution. Right? Right? Right, only one solution, that is one point at which these lines intersects. For example, if we take this system of equations, x1 plus 2x2 equal to 4, 2x1 plus 4x2 equal to 8. If we try to solve, actually if you see here, if you divide the second equation by 2, it is nothing but the same, right? x1 plus 2x2 equal to 4. These two represent only one system, right? Okay. Now, if we try to find the solution in the sense here, the values of x1 and x2 which satisfies, right? Suppose if we put x1 equal to 0, we'll get x2. If we put x2 equal to 0, we'll get x1. If we put x1 equal to 1, we'll get x2. Like, so how many we'll find? So we'll find many values or many combinations for x1 and x2 which satisfies this system. So that means when we plot, we'll get, so both lines combines and forms only one straight line. So how many points are there which satisfies both? Infinite, right? So whereas here in this case only one point. Therefore, this is called as unique solution, right? Unique. And the second one, how many are there? More than one, right? So infinite number of solutions or infinitely many solutions or more than one solution, what we call as, right? And third case, if we take x1 equal to 2x, x1 plus 2x2 equal to 3, 2x1 plus 4x2 equal to 8. Right? If you see here, actually, if you draw these two lines, they are parallel lines. Or otherwise, if you see slope of these two lines, both are the same. The slopes are equal, then lines are parallel. If lines are parallel, then they are not going to intersect anywhere. Right? That means no solution here. Right? No intersection means they won't join. That means there is no point where both coincides. That means there is no solution for this. Right? Otherwise, if you see here, if you multiply this first equation by 2, 2x1 plus 4x2, actually we have to get 6, but we are getting 8. Right? So that means when we try to attempt or when we try to solve non-homogeneous system of equations, we may encounter any one of these cases, either unique solution, here infinite number of solutions, or infinitely many solutions and no solutions. So that we have to keep in mind whenever we try to find solution of system of equations, we get any one of these cases, either we may have unique solution or infinitely many solutions or no solution. Right? So when it happens, we'll see it. Right? So next is homogeneous. Right? Homogeneous as seen at the beginning, it is nothing but Ax equal to 0, right? Right? You won't have the constant terms, right? Right? No constant. Now, if I ask a question like this, so what are the values of x1 and x2 which satisfies both equations, right? What are the values of x1 and x2 which satisfies both equations? Suppose if I ask, right, immediately we understand. If we put x1 equal to 0 here, I think x1 equal to 0, here it is x2 equal to 0. So both satisfies, right? That means for homogeneous system of equations, always there exists a solution, which is we need not find it actually, default. So by virtue of its nature itself, always it will have a solution which is zero solution. Why zero solution? As already seen, right, as discussed, both passes through origin. If you take any homogeneous, any homogeneous, they passes through origin. So that means origin is always a point of intersection for them. So then what else we have to do? Right? So whenever we try to attempt the solution of homogeneous, so we have to see, is there any possibility of having non-zero solutions? Right? Non-zero solution means, is there any x1 equal to 1, x2 equal to minus 1, which here in this case if you take x2, x1 equal to 2, x2 equal to minus 1, possibly it may become 0, right? Right? So that means we have to, whenever we try to solve homogeneous system of equations, we have to keep in mind, so we are trying to check whether the given system is having non-zero solution or non-trivial solution, right? That's why here there won't be any case saying that solution doesn't exist. That means inconsistence, what we say. Right? There won't be any case which says the system is inconsistent when we try to attempt homogeneous system of equations. Right? So I hope that this is clear, right? So that is, so linear equations, then the linear equations we categorize into homogeneous and non-homogeneous. In case of homogeneous, three cases we'll have. One case there won't be any solution. In other case, there is a possibility of having solution. It can be unique solution or infinitely many solutions. Whereas in case of homogeneous, this is always there, right? So only thing is we have to check for, is there any bonus solution, that is non-zero solution or non-trivial solution, right? So how to? So here to solve, while solving the system of equations with the help of matrices, here we'll take the help of the concept, that is here it is rank of a matrix, which we discussed in the earlier sessions, right? So rank is the one which helps us to solve the system of equations or to understand the system of equations, right? So here this slides explains the whole scenario related to the complete system of equations which are linear. If you see here, just I'll go through this, then we'll try with one or two numericals. So linear equations, right? So non-homogeneous, or it can be homogeneous. That is, ax equal to b is non-homogeneous as discussed, or ax equal to 0 is homogeneous. And we have seen two instances happens. One is the system may be consistent or the system may be inconsistent. Inconsistent means solution exists. Inconsistent means there won't be any solution. Right? So when we say a system is consistent, when we say the system is inconsistent, the rank of AB, here I think B is this small b you can consider. So that is augmented matrix. Rank of augmented matrix equal to rank of A, then the system is consistent, that means solution exists. If these two are not equal, that is rank of augmented matrix is not equal to rank of coefficient matrix, then the system is inconsistent, that means no solution. That is third case what we discussed earlier. Okay. So then based on this, if it is inconsistent, simply we'll stop there and we say there is no solution for the system of equations. If it is consistent, we'll go down and see what type of solution it will have. As discussed, it may have unique solution or it may have infinite number of solution. So as we mentioned here, rank of AB equal to rank of A. If it is equal to number of variables, then it will have unique solution. That is first kind of solution what we discussed. Suppose if rank of AB equal to rank of A less than number of variables. Variables means, you know, right, in the X column vector, what are the variables? How many variables are given? That is n here. If it is less than n, that is number of variables, then the system will have infinitely many solutions or infinite number of solutions, right? So next, coming to homogeneous, so trivial solution, so we need not check. So only is thing is, if rank of the coefficient matrix equal to n, it will have only trivial solution. That means there won't be any bonus solution for it. Right? So we have to stop there and says there is no bonus solution. There is no trivial, non-trivial solution for this. If it is less than n, if rank of that coefficient matrix is less than n, then we say the system is having non-trivial solution. So this is how we try to understand the system of linear equations, which are of two types, homogeneous and non-homogeneous. Okay. So with this understanding, what we do is we'll try to solve a problem. Okay. Very simple problem. Very simple problem we try. So that will become convergent with the process. Right? So solve the following system of linear equations: x1 plus x2 equal to 3, x1 minus x2 equal to. So immediate idea that what we have to get is it a homogeneous or non-homogeneous? Right? So because here the constants are there, right? So this is non-homogeneous. Right? Non-homogeneous, right? So that actually here itself we have to have clear understanding regarding what we are going to do further when we try to solve a problem. So non-homogeneous, immediately we have to remember non-homogeneous means, so we'll have consistency and inconsistency, right? Consistency, that means solution exists or no solution. Then what are the conditions? Here rank of AB, that is a augmented matrix, equal to rank of A, right? So then the system is consistent. If it is not equal to, then inconsistent and there is no solution. So immediately after seeing this, we have to get this idea in mind. So then we can proceed further. So when we proceed further, only thing what we have to do is, already we are aware of when it will have, when the system is consistent, when the system is inconsistent, right? Only the idea what we need to have is finding the rank of a matrix, right? That's it. It depends on finding the rank of a matrix, right? So first step, so we convert this, or we write this in the form, in matrix form, where the coefficient matrix 1 1 1 minus 1, and B is 3 1, and X is x1 x2. Right? So A is the coefficient matrix, X is the column matrix consisting of variables, and this is B matrix. So next we need to take augmented matrix, right? Augmented matrix is, so A and together with B, that is extension kind of thing. A with B. So this is A and this is B. Right? So next we need to find the rank of a matrix. So how to find the rank of a matrix? We will find rank of a matrix with the help of that echelon form which we discussed earlier, echelon form. So even in the earlier session also we discussed when we tried with the Hermite form, right? Same way. So first what we have to do, if you remember, so principal diagonal, then we have to convert it into upper diagonal matrix, etc., etc., right? So we have to convert the given matrix into echelon form, then we'll try to find rank, corresponding rank. So first what we do is we'll try to make this as 0. Right? Only row operations, column operations are not allowed, right? So because it involves transformations, right? Ax equal to b, so you cannot go for column operations, or otherwise in the echelon form itself imposes a condition saying that only row operations are allowed, right? So here row operations, what we do is we want to make this as 0, right? So we go for R2 is R2 minus R1. Right. So 1 1 3, R2 1 minus 1 0, minus 1 minus 1 minus 2, 1 minus 3 minus 2. Right. Okay. So this is what. Now, so we'll check, is it in echelon form? Right. Now is it possible for us to make this as 0? No, right? When we try to, suppose if we try to make this as 0, we have to go for row operation with this only. When we go for row operation with this, then this comes here and it becomes non-zero, which we don't want, right? That means we have to stop there and say that this is in the form of almost like echelon form. Right? So then we'll take the rank. So if we consider the complete matrix, which is in echelon form, and this is a non-zero row, this is a non-zero row, therefore rank of B means here augmented matrix, or we can take it as AB, whatever it is, right? So rank of augmented matrix equal to 2. Then we need rank of A, right? So this part is A, always it carries. So this part is A. This is a non-zero row, this is also a non-zero row, therefore rank of A is 2, right? So that means rank of AB equal to rank of A, that is 2, right? And immediately we understand whenever rank of augmented matrix equal to rank of coefficient matrix, the system is consistent. Consistent means solution exists, right? There is a solution. Right? So immediately the idea comes, solution is there means is it going to be unique or is it going to be infinitely many solutions? So then immediately number of variables x1 x2, that is 2, right? So rank of A augmented matrix equal to rank of coefficient matrix equal to number of variables, therefore unique solution. Right? Sometimes in exams they may ask us to discuss the nature of the solution, right? Or discuss whether the system is consistent or inconsistent kind of. Then simply we stop here. We have to stop here. The system is consistent because rank of augmented matrix equal to rank of A equal to number of variables. It will have unique solution. That's it. Suppose if we want to find the solution, then we have to solve the system of equations. Right? How to solve this? Whatever we have done in the beginning, where we converted equations into matrix form. Now we convert this matrix into equations. Very simple. This is A, this is B, right? So x1 plus x2 equal to 3. And second one 0x1 minus 2x2 equal to minus 1. Right? So minus 2x2 equal to minus 1, x2 equal to 1. So from this we can have x1 value. Right? So x1 equal to 3 minus x2, that is 2. Right? So we got the unique solution. Okay. So very simple, right? If it is infinite in number of solutions, then we will also solve it in the same fashion. Right? We'll see. We'll try with 1 or 2 examples. Right? So similar simple example. Right? Solve the following system of linear equations: x plus y equal to 3, 2x plus 2y equal to 7. So same immediate idea that what we have to get is non-homogeneous, right? Non-homogeneous. So why non-homogeneous? It's very simple, right? So because of this, because it is in the form of A, that is solution exists and inconsistency. Right? Coefficient matrix is 1, 1, 2, 2, and this is B matrix. Right? Okay. So we wrote it as AX equal to B. Right? So augmented matrix where A and extended with B. So that is augmented matrix. So 1, 1, 1. This is A part and this is B part. So again the same thing, we have to go for echelon form of the matrix. So we try to make this as 0. So where R2 is, row 2 minus 2R1. 2 into this row and minus this. That is R2 is R2 minus 2R2 in reverse. So then we'll get this. So now if you say we are now, so this is 0, see what are the ranks of augmented matrix. So this is that is 1. So then rank of AB is not equal to rank of A. Rank of AB is not equal to rank of A. That means we remember the condition. That is system is inconsistent. That means there won't be any solution for this. That is last case. Now the outcomes, how to remember this. Suppose we fail to remember these cases, rank of AB equal to rank of A, like, then also no problem. Suppose ignore this, then try to solve the equation. Once we are having echelon form, if we try to write the equations here, what we get is x plus y equal to 3, right? And second one, if you see 0x plus 0y, 0x plus 0y equal to 1, right? So 0x plus 0y equal to 1 means now you can see this is nothing but 0 equal to 1, which is observed, right? Observed means no, conclude with respect to the nature of the solution, right? So with that understanding, then we'll try with a little bit a bigger system where three variables are involved, x, y, z. Then we'll see what happens. Right? No need to repeat it, right? So this is very important at the beginning. Whenever we see or whenever we try to solve the system of equations, first thing we have to identify is it a homogeneous or non-homogeneous. If it is a homogeneous, then generally we'll think of non-trivial. Otherwise, if it is non-homogeneous, then we have to think of the three kinds of solutions. Okay, right. So now we'll write these equations in matrix form. Right, coefficients 1, minus 1, 1, 3, minus 1, 2, 3, 1, 1, and this is B. Right? We'll see it. So A is the coefficient matrix. A is the matrix with, I think, one more is there, x, y, z. Right? So three variables, and B is this. Okay. So then augmented matrix. So A and this is B. So now if you remember, so now we are trying to convert this into echelon form. So then this is diagonal, right? So if you remember what we have to do is we have to convert this into upper triangular matrix. That means echelon form, while to have echelon form, what we need to try is we have to make this as almost like an upper triangular matrix. So that means we have to try with row operations to make this as 0 and this as 0. Only row operations. So now generally we'll do like this. R3 will go with R1, right? So R2 minus 3R1 is 1. So to make this as 0, we go with again. So it is R2 is R2 minus 3R1, R3 is R3 minus 3R. So then we'll see what happens. So I think here the rough work is also done. If any doubt, we can go through it. So here, so what we get is after the operations, these are the operations, then we'll get, so 1 minus 1, 1, 2, this is, right? But still it is not in echelon form, right? So if you see this is the diagonal, right? So still this, right? Now we have to make this as 0. How to make this as 0? Whether we have to go for operation with R2 or R1. Generally always that doubt comes in mind. Right? So whether to go for operation with R2 or R1. If we go for operation with R1, that to row operation only allowed, right? Then this 0 becomes non-zero, which we don't want, or it is not the required thing, right? That's why we avoid that operation. So we go for this. That is R3 minus 2R2. Right? R3 minus 2R2. So that this becomes 0. Okay. So this is what we are getting. So here the clear calculations are done for the sake of understanding. So this is 1 minus 1, 1, 2, this what. Now check, is it in echelon form? Yes, if you see here. Right. So this is the diagonal. Right. Okay. So now the matrix is in echelon form. Once it is in echelon form, then rank, we look for rank. So the whole thing is rank. Augmented matrix, we need rank of the augmented matrix, right? So then immediately non-zero, this is non-zero row, this is a non-zero row, this is a 0 row. 0 row means all elements are zeros, that is. Right. So in echelon form, the rank of a matrix is number of non-zero rows, right? This is 1, this is 2, therefore rank of augmented matrix equal to 2. Clear? So then this part is A, right? This part is A. This part is A. So here also this is non-zero row. This is non-zero row. This is 0 row. That means two non-zero rows are there in the coefficient matrix. So rank of A is also 2. So rank of AB equal to rank of A. That means immediately we understand that this system is consistent, right? Consistent, right? Consistent. Consistent means solution exists. Then we have to see, is it going to be unique solution or infinitely many solutions, right? So then we'll see number of variables. Here if you see the given problem, it contains three variables. Number of variables are 3 x, y, z, right? So three variables, right? So rank is 2, variables are 3, less than, therefore system is consistent with infinite number of solutions, right? If only nature is required, so we'll stop the discussion with this. If we want the solution, we have to extend it further. So extend it further means we have to write, or we have to convert, or you have to write this matrix in terms of the regular format, the equations format. It is x minus y plus z. This is a b, right? So right hand side. So and 0x plus 2y minus z equal to minus 12. Right? Now how to solve here, right? That is the first. Now if you see here, three variables are there, right? 1, 2, 3 and two equations are there. Three variables and two equations. Then our solution will contain one parameter, right? One arbitrary constant or one parameter, right? Suppose it won't apply here. Suppose second equation is not there, only first equation is there, right? That means three variables but only one equation, right? Then our solution will contain two arbitrary constants, right? So it won't apply here because it is two are there. That means what we have to do is we have to assume one of the variables as constant, some k. So either here we can take y as k or z as k. Let us, anyone you can take. Accordingly, we'll have our solution. Here solution is not going to be the same, right? Because it is what we say infinite number of solutions, right? Okay. Now we had y and z. So where k is an arbitrary constant, if we put k equal to 1, we'll get one solution. K equal to 2, another solution. K equal to 3, another solution. K equal to minus 1, another solution. Like, so that means how many values that we can give to k? Infinite number of values. How many solutions will have? Infinite number of solutions. So that's why we say the system will have, or system is having infinite number of solutions, right? So I think we covered three kinds of. First one is unique, next one is inconsistent, that is where there is no solution, and third one is infinite number of solutions. Right? So now another problem of different kind, but the concept or the idea what we are going to use is the same concept, right? So here this is in general it is a regular kind of question appears for many of the examinations, either regular examinations or competitive examinations. Right? So for what values of lambda and mu, the system of equation mu, it will have all the three cases. So because it is a non-homogeneous system, right? So therefore for what values of lambda and mu, it will have no solution, it will have unique solution, it will have infinite number of solutions. Right? So approach is the same approach, same understanding, same concept. So there is no deviation at all. So first, as usual, what we have been doing here also, the same thing we have to do. That is, first write in the system, the matrix form, where A is this, right? Where lambda comes 1, 1, 1, 1, 2, 3, 1, 2 lambda. So here 6, 10 mu comes as B. Okay. So A is this, and x is our xyz, and b is this. So immediately what is the next step? Augmented matrix, right? So augmented matrix. So this is A and this is B. Same flow, same process. Right? So next, immediately what is the next step? So echelon form. So for echelon form, immediately what we see is the diagonal, right? let us try to make the elements below the diagonal as zeros first. Then depending on the situation, we'll try to extend it further. So here, so try to make this as 0. Try to make this as 0. Same, accordingly we have to go for row operations. So R2 is R2 minus R1. R3 is R3 minus R1. Right? So then we got this. Right? So no change, no change. So next, whether we arrived at echelon form, let us see. Right? So still this is there, right? So we have to make this as 0. How to make this as 0? Same like as discussed earlier. So whether to go with R1 or R2. So if we go with R1, what happens? Already we discussed. Otherwise here we have to go with R3 is R3 minus R2. Okay. So then we'll get this. Right? 1, 1, 6 this. Now if you see here whether we arrived at yes. Right? So this is almost like echelon form. We cannot say that is almost like the form which we are trying for. Now here if you see the rank of this depends on these values, right? Very simple understanding, right? If it is 3, it becomes 0. If it is 10, it becomes 0. Then rank will be different, right? So that is what they are expecting, right? So we need to try with different combinations for lambdas as well as mu's. Then accordingly we have to see what is the rank of A, what is rank of B, then what is the conclusion. Okay, so here if you see suppose lambda is 3, 0 and mu some value which is not going to become 0, right? Now we'll see what is rank of A. So this is A, right? This part is A, right? This part is A, right? And this is a non-zero row, this is non-zero row, this is 0 row, right? That means rank of A is 2, right? And this whole matrix is the augmented matrix, right? And in this is non-zero row, this is non-zero row, this is also non-zero row because this is not equal to 0, right? One element is enough, right? This is not equal to 0, therefore rank of AB is 3. Right? That means rank of AB is not equal to rank of A, inconsistent, therefore no solution. So like this we have to try for various possible combinations for lambda value as well as mu value. Okay. Now another case. So suppose lambda is not equal to 3 and mu can be any value. Right? Suppose lambda equal to 3. Right? So lambda is not equal to 3. Lambda equal to 3 already we discussed. Lambda is not equal to 3, then means this is not equal to 0. Right? Then if you see, if you take the complete matrix, mu can be any value. This is a non-zero row, this is a non-zero row. Irrespective of this value, here already non-zero value is there, therefore it is non-zero. Right? So therefore rank of AB is 3. Number of non-zero rows 3, therefore 3. Then if you take this part, this is A, right? So this is non-zero row, this is non-zero row, this is also non-zero row. So rank of A is 3. So rank of AB equal to rank of A. That means what we say? Both are equal, right? That means consistent. So if it is consistent, immediately we need to say whether it is unique solution or infinitely number of solutions, which it depends on number of variables, right? So here number of variables x, y, z 3. So all are equal, then it is unique solution. Okay. This is second case. Now third case. If both are zeros, then what happens? That is the question. Right? That means if lambda equal to 3 and mu equal to 10, so then this becomes 0, this becomes 0, right? This is what we get. Now if you take the complete matrix, there is augmented matrix. So this is non-zero row, this is non-zero row, this is 0 row. That means 2 non-zero rows are there, therefore rank of augmented matrix equal to 2. And if we take the A matrix, this is non-zero row, this is non-zero row, this is 0 row. That means 2 non-zero rows are there, right? That means rank of A is 2. So again the same, right? Rank of A B equal to rank of A, therefore consistent, right? That means yes, 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 solution exists. Right? If solution exists, then what kind of solution we expect? So then it depends on number of variables. So number of variables 3, rank equal to 2, therefore it's less than, therefore it will have infinite number of solutions. Right? Okay. So this is how one is directly solving and the other one is trying to find the types of solution which depends on the unknowns lambda and mu given in the system of equations. Right, so that is about non-homogeneous. So that's why we have to see the requirement. What is that they are looking for? If it is only nature, then we'll compare ranks. Based on the ranks, we'll conclude whether the system is consistent or inconsistent. Then unique solution. What is Z value? Okay, so that is all about the non-homogeneous system. So let us try with a homogeneous system also. One example, right? So here very easy to say, right? So no B here, B equal to 0. So again I repeat, here there won't be any inconsistent case. Always homogeneous system is consistent. Always homogeneous system is consistent. Why it is consistent? Always it carries a solution which is x equal to 0, y equal to 0, z, or x1 equal to x2 equal to x3 equal to x4 equal to 0. So the always consistent with the trivial solution or zero solution. Only thing what we are trying is we are trying to find is there any other bonus solution for this, extra solution or bonus solution for this non-trivial solution. Okay. So quickly we go matrix here. And so same way we'll go for echelon form of the matrix. So same, so diagonal elements, right? This is diagonal. This is diagonal, right? So now we'll try to make this as 0, this as 0, this as 0 first. So same R2 is R2 minus 2R1, R3 minus R1, R4 minus 4R1. So first this operation, we try to make these elements as first elements as zeros. Then we got it, right? 0, 0, 0. So again we'll see whether we got the echelon form what we are looking for. Right? So again this is there, right? This is there, right? Already this became 0. Otherwise we have to make this as also, this also as 0. Now, so what is the suitable operation? R4 with R2 is better, right? So therefore R4 is R4 minus R2. Okay. So if we go for R4 minus R2, then we got this. Okay. Now still if you see here, okay, actually it is there. So then the question comes, actually once we got this, then we have to see whether we had increasing number of zeros before a zero. That is actually one requirement what we look for in echelon form. So we won't proceed as it is. Here if you see for a this is a non-zero, right? Here we had 1 0. Here this is a non-zero element, right? So before that 3 zeros are there. So here this is a non-zero row, non-zero element in that row at the beginning. So before that 2 zeros are there. So 1, 3, 2. Generally we expect it to be increasing number of zeros before a non-zero element, right? So then what we can, very simple, we go for transformations, interchanging of R3 and R4, right? Interchanging R3 and 4. This row goes there and that row comes here. Then it perfectly fits 1 0, 2 zeros, 3 zeros. Right? So now this is in the required form, that is required echelon form of the matrix. Now what is the rank here? What is the rank here? So this is non-zero row, this is non-zero row, this is non-zero row, this is non-zero row. So rank is 4. Then it depends on number of rows, right? And number of unknowns. Here the given system contains x1, x2, x3, x4, that is 4. So rank equal to number of unknowns. Therefore it will have only trivial solution or only zero solution. So there won't be any other solution for this, right? Okay. So we'll see one more because it is a trivial. We'll see whether maybe next one is going to be non-trivial solution. Okay. Yeah. So if it is non-trivial, what happens? We'll see with one example. So very simple, the same process, same approach here. If you see B is 0, right? B is 0, therefore it is homogeneous system. So then we'll take the coefficient matrix A, then we'll convert this into echelon form with the help of suitable row operations only. Right? So you see here. So making this as 0, making this as 0, making this as 0 with the help of row operations, right? So I'm not going to explain this, already the work, rough work also done here. So now if you see here, after these operations, this is what we are getting. Now we'll try to make this element as 0 and also this element as 0 with, again with the help of row operations. So just this is a continuation of the same, so where we'll try to make, or we try to convert this into echelon form. Just you can go through it, very simple. Right? So now if you see here, this is the final echelon form of the matrix. Right? You see here. Right? So it perfectly echelon form. Now if you see, this is a non-zero row, this is a non-zero row, right? So rank of matrix is 2 non-zero rows it is having. Therefore rank of A equal to 2. But number of variables are 4, right? x1, x2, x3, x4. So this rank is less than number of rows. Therefore it will have a non-trivial solution. So now the question here is how to find the non-trivial solution, right? So how to find the non-trivial solution? The same like what we tried with the non-homogeneous system of equations. So go back and write this in terms of equations, right? So here if you see, this is x1 minus x2 minus 2x3 plus 3x4 equal to 0. And this is 0x1 minus 3x2 plus 3x3 minus 4x4 equal to 0. Right? Now we have to solve this. Right? How to solve this? Like what we tried in case of infinitely many solutions when we discuss non-homogeneous case, right? Similar kind of. Here if you see how many variables are there, 4 variables. How many equations are there? 2 equations. That means our solution contains 4 minus 2, that is 2 constants or 2 arbitrary constants. Right? It is similar to what we tried there. Right? So you can take arbitrarily anyone, but not x1 here from the second equation, right? So you can take either any one of these 3, any 2 of, because it is 2, right? Any 2 of these 3 variables as some constant. So here I took x2 equal to k1, x3 equal to k2. So x2, k1, x3, k2, from that we'll get x4 value. That means we had x2 value, x3 value, x4 value. If we substitute all these values here, we'll get x1. Right? So finally, the solution, that is x value, x1 value, x2 value, x3 value, x4 value, contains 2 arbitrary constants k1 and k2. Right? So this is how we solve homogeneous system of equations. Right? This is final solution. And just before summarizing, just we'll try to discuss one theorem, very simple theorem. If A is a n by n non-singular matrix, n by n non-singular matrix, then the system Ax equal to B will have a solution. Right? So Ax equal to B is nothing but non-homogeneous system of equations, right? And where the condition here is A is a n by n non-singular matrix. Non-singular means we know, right? That is, det is not equal to 0. So immediately we say when det is not equal to 0, the inverse of the matrix exists. That is, A inverse exists. Right? Now this is the system of equations, right? So now what we do is pre-multiply this system by A inverse. So then A inverse AX equal to A inverse B. Now we know associative property, right? A inverse into A we can combine, right? By using associative property. And this A inverse A is nothing but identity matrix, right? This is identity matrix. So identity matrix product with any matrix gives that matrix. So I into X is X. Then X equal to A inverse B, where X is nothing but the solution, right? That means whenever this matrix is a non-singular matrix, then the system of equations Ax equal to B will have a solution, right? This is one theorem, right? So one more theorem, actually this is already what we used to solve the system of equation. That is, when rank of the coefficient matrix equal to rank of augmented matrix, then the system will have solution, right? This is one of the fundamental theorem which is very important, and we'll take this for discussion in the coming sessions. So before closing, we'll summarize. So what we discussed today is, what we need to understand from today's discussion is, so system of equations, that is, which are linear equations. So we understood this in two categories. One is Ax equal to B category, that is non-homogeneous, right? And other one is Ax equal to 0, that is homogeneous category, right? So homogeneous category will have two kinds of solution. One is zero solution, other one will have non-zero solution. So then how to find it? It's based on the rank of the matrix. Rank of the matrix equal to number of variables, then zero solution only, that is no bonus solution. If rank of the matrix is less than number of variables, then we will go for non-zero solution. So coming to this, three kinds of, so maybe it is a unique solution, or it may be the case where we'll have infinite number of solutions, and other one is no solution, right? No solution. So these two together, what we say is consistent. These two together comes under consistency. So when it happens, rank of AB equal to rank of A, rank of augmented matrix equal to rank of A, so then it falls under this consistency. If rank of AB is not equal to rank of A, then it falls under inconsistent, that means no solution. So if it is consistent, then we'll dig further and see whether it is unique or infinite, which depends on number of variables. If rank of AB equal to rank of A equal to number of variables, then unique solution. If otherwise, it will have infinite number of solutions. So this is how we can understand the solution of system of equations which are linear. Thank you.